Okay.
It's recording.
Wait, do I need to start my Audacity?
No. We're not doing that anymore. It's a lot easier now.
Oh, we're not doing that. Oh, okay.
Thank you, though, for thinking of that. All right, guys, welcome to the Ozeki Journal Club. I'm Carlos. Hey, Perry.
I'm Perry.
That's Perry over there, and we got we got Simon Sehayek here back to join us, our most loyal guest of the show. Let's put it that way.
Hello.
Repeat guest.
How's it going, Simon? Happy New Year.
Thanks, man. Happy New Year.
Oh, Happy New Year to us too. Thanks, Simon.
Yeah, that's what I meant.
Well, it's 2021, and the podcast is alive and well. I don't know if we should keep calling it a podcast because it's really just YouTube videos, so it's maybe like a YouTube channel.
Yeah, that sounds more like.
I wanted it to be a podcast.
How many views do you guys?
Honestly, we range from like 80 to 10 views on each video.
But we started with the upper.
We're just getting started, Simon. All right, Joe Rogan. Joe Rogan is he's in his 1500s episodes, right? 1500. So we're on episode like 20. Right. If you got 1% of Joe Rogan, we're good. All right. So today, again, we're sort of spreading out what we're interested in and talking about some research related to COVID. Simon, you are the closest thing we have to ACS Nano, since you have a paper in ACS Nano. So we invited you to discuss this paper. I mean, I'll give the title, and I think you're going to take the lead. You're going to walk us through it, eh?
Doesn't have anywhere near the impact that this.
Yeah, this one has a crazy amount of views, eh? Had like 300,000 views or something.
Yeah, it's crazy. Yeah.
Okay, well, let me give the title. We can talk about it. So the title is Aerosol Filtration Efficiency of Common Fabrics Used in Respiratory Cloth Masks by Abjeta, Konda, et al. Gregory Grant, Supartik Guha. I don't know where they're from, actually. I didn't check. And it's published in ACS Nano. All right. So, yeah, Simon, you want to walk us through it?
Okay. You want me to do this? Okay. So basically, they studied mask efficiency based on material and like as a function of aerosol particle size. And I guess this is obviously related to COVID-19, right?
Yeah. It was written like with COVID-19 in mind, even though there's no COVID in the title, right?
Yeah.
It's April 24th, 2020 is when it was published. Yeah. Look when it was received. April 18th, it was received, accepted 21st, published 24th. Wow. 6 days.
That's crazy.
How crazy is that?
Over. That's crazy.
Did you see that GIF I sent?
If you just scroll down, Simon, you'll see it, the dates.
Did you guys see that GIF I sent of COVID papers getting reviewed? It was like this video of someone doing like security checks, and they're walking through with like machine guns and like, all right, you're good. Papers getting reviewed for COVID.
But to be fair, this was like really well written, I found.
Yeah, it was really nice.
But it was 6 days between receiving the paper to publishing it.
I've never seen that.
Nuts.
But it was solid. I didn't have many notes.
Sure.
So yeah.
So I don't know your view, like what your audience is here. So I guess for clarification, COVID-19 or SARS-CoV-2 is the current pandemic that has taken the world by storm in 2020, and we're still not out of the woods yet. Is this what I should be saying?
Yeah, that's good. I like the context.
Okay, perfect.
And also, what's nice is that this was a controlled experiment, right? So I think a lot of the stuff that's coming out is not really like easy to, I guess, learn from, because you don't really, there's so many like factors involved, and they tried to really like mechanically and physically study what's going on. So I think for me, that was one thing I wanted to read more about.
Although like real life
is not
implications. Yeah, it's hard to know what the real life implications are.
But you have to start from this, I find. Like
I think they did a good job of comparing it to real life, honestly. The experiment is controlled enough, I find, that you can actually gain something useful to describe real life.
Right.
With. So anyways, we should probably get into what they're
let's get into it.
Yeah, so basically, so one big thing about this paper is, and guys, please fill in if I leave some gaps. No pun
Yeah, I have
intended.
my own
And
highlighting.
I guess the audience doesn't know what I'm talking about. Yeah. But yeah, so basically, the idea here is, so there's, okay, I guess we'll talk about this a bit later, but there's, for smaller aerosols, so the physical barrier of the mask is obviously not enough to impede the particles from getting expelled, but at that level, electrostatic filtration becomes more important. And so they were thinking of using these hybrid masks, or testing these hybrid masks to see what their efficiency is for letting aerosols through, again, as a function of aerosol size. So yeah, so do you guys want to say something? I don't know.
Yeah, no,
that's
fair.
Something?
Yeah, I think the point is, yeah, you can obviously expect filtration to be better as you increase or decrease the size of the holes between the fibers of your mask. But at one point, the particles are so small that you can't decrease the size anymore. So you need a different way of stopping these particles from getting through. And a different way that you can use is using electrostatic or filters that have some electrostatic forces that can capture the particles.
Although one thing that they bring up as a caveat is that it's not well understood, like what size of particle is or size of aerosol is relevant for COVID transmission.
But they give a quite a large range, though, right?
Yeah, for sure. But I mean, we don't even know like at what size it's transmitting, right?
I guess that's true.
What size of
aerosol? So they say they say order of magnitude. Oh, sorry, order of magnitude. They say 5 microns for respiratory infection, infectious diseases. But
yeah, they know for other ones.
We don't know.
I mean, they study between 10 nanometers.
So they study
10 nanometers and 6 microns, I think, right?
Oh, 300 nanometers and 6 microns.
Sorry. Oh, maybe. I guess we'll get into it.
Oh, I think you're right, actually, Perry. Yeah, it's 10 to 6.
It's 10 nanometers to 10 nanometers to 600 nanometers, basically.
10 nanometers is really tiny. Or
6,000 nanometers.
Yeah, 6,000.
10 nanometers is freaking small, though.
So
how big is the virus?
They cover the whole range.
But like, it's not.
I think the virus is 10 nanometers.
Yeah, so it's crazy. But if they're not, oh yeah, they go from 10. 10 nanometers is the whole virus. So if it's in a droplet, it's going to be like, I don't know, much bigger, right?
I mean, I think the droplets are covered within the range they give, right?
Yeah, they are. I mean, also they distinguish between droplet and aerosol, I think, right? The micrometer range is more.
Oh, sure.
Droplet.
Yeah. So droplets, aerosols are just small droplets.
Should we go?
Yeah.
Sorry, Simon, you're leading the show.
Right. So wait, so should I call, what are the larger droplets? Are they also aerosols, or are those like micro droplets at that point?
I think the distinct.
What's like the correct?
Go ahead, Carlos.
I just think there's a point where they don't call it an aerosol anymore, and they just call it a droplet.
Yeah.
Because I think the droplets fall to the ground, and the aerosols just stay floating for a long time.
Right. So
3 hours, they said, actually,
I guess
the aerosols. They said they
for COVID,
float up to 3 hours. It's crazy.
Yeah, that is crazy. So should I go through this?
Yeah, let's look at this contraption.
So what is the experiment they're doing? Yeah.
So basically, they, from what I understand, okay, very simple. They put air in this chamber, and they flow it through this thing here, where they have the whatever fabric they're testing, right? And it flows through this tube, and basically they measure the concentration in this chamber, so that's what they call upstream, and they measure the concentration in this tube, which is the downstream concentration. And they have two different contraptions for detecting which particles are getting through and for detecting which what size these particles are. So this OPS is one of those, and the nanoscan is another. And so the nanoscan measures between this 10 to 300 nanometer range, and the OPS measures from 300 nanometers to 6 microns. Is that correct? What I said?
I think so. Yeah.
I think so.
I mean, one of them is for the big ones and one of them is for the small ones, right?
Yeah, so 10 to 300
Exactly.
and 300 to 6.
Yeah. I think nano is for the nanometer scale. Nanoscan.
There was something a bit weird, like with the nanoscan, where I think they were missing some of the range from like 178 nanometers to 300 or something. So it was measuring it. Oh, okay. Well, anyway, guess we'll get to that. So yeah, and I guess they also measure the pressure difference and between these two chambers, and I guess the idea is, if the pressure difference is greater, it's less comfortable to wear, right? So
And the velocity of the particles also they measure.
Yeah, and the velocity of the particles. So yeah, I think they tested two different velocities. They tested I don't know what these units are exactly, the 1.2 CFM and the 3.2 CFM, but they say, so one of them is 35 liters per minute, which is the 1.2, which is like resting breath rate, and then there's the moderate exertion, which is 90 liters per minute. So that's their faster velocity.
Mm-hmm.
And that's, and just to be clear, the particles we're looking at are like sodium chloride particles, right?
It's just salt water.
Yeah.
Wait, is it in water? Yeah.
I think it's just.
Or is it just the sodium particles?
That's a good question. I'm not sure, but
I tried.
It says a polydispersed sodium chloride aerosol is introduced into the mixing chamber.
They do not mention water more than once.
Yeah, there you go.
So yeah, maybe it's just those raw particles.
I mean, maybe a droplet though. Maybe it's a droplet made from water and sodium chloride. Right?
Yeah, I guess.
It's probably, that's what I assumed.
Okay.
I tried to look at this. I didn't really understand what this particle generator, how it works exactly.
Sounds fancy.
And I guess also something I might, they have these adjustable holes on this tube to kind of emulate mask fitting. So if your mask isn't fitted properly, one of these holes, I guess they'll unblock it to let the air flow back into the chamber. And
oh wait, that's weird.
I didn't.
I thought the hole would be like at the level of the mask, right? Somehow.
Yeah, but you see, this tube is in the aerosol mixing chamber.
Yeah.
So it's like the hole lets you bypass the mask, as if there was a hole on the side of your mask, so that the particles can get through.
Yeah, that's true.
They're trying to simulate what a real life environment of wearing a mask looks like, right?
Okay, that's neat.
You have a mask with some holes potentially. Because
holes, you mean like not necessarily like holes in the fabric, but holes in like
it's not fitted to your
stuff
face.
sticking out. Yeah.
So I think these holes were like 0.5% to 2% the surface area of the mask they were testing.
Mm-hmm.
There's 59 centimeters squared here.
Mm-hmm.
So and they got pretty significant results when the holes were active, of the concentrations going back. So I guess the point is, fitting is pretty important when wearing a mask.
Yeah.
And so let me see if I missed anything. Yeah, so as Carlos said, they think aerosols for COVID stay in the environment up to 3 hours. And I guess less than 1 micron. I guess for general respiratory infections, they say they can last up to 8 hours. So I guess they don't fall due to
Sorry to cut you off, Simon. I just realized you wanted to say that before we started, we're just reading a paper. We're not trying to make any health recommendations or anything like that, right?
Oh yeah. We're not experts in
We're not health
this
experts
field. We're just
at all.
We're curious. We're just curious readers.
We're just curious boys.
And we all have a background in science.
That's it. We're reading this as scientists.
If that helps.
Sounds good. Thanks. Okay, sorry to cut you off. Go for it. Just to get the lawyers off my back. Yeah. That's it.
Can you?
My lawyer's already calling me.
Could you take that segment of the podcast?
No way, I'm not doing that. It's gonna take me like half a day.
Okay. Okay. And did you guys want to add anything to what I said?
I don't think I have anything to add. I guess we should get into like what the results were. The charts were interesting.
Yeah, I think it's cool that they looked at like I said, they're trying to simulate real life, right? So you have a mask with holes that potentially give you like not fitting properly, and the velocities that are directly corresponding to like you breathing normally or you breathing like after jogging a bit or something, you know?
Mm-hmm.
Like these are real life environments or conditions that you would want to see if a mask works or not.
Mm-hmm.
Yeah.
So I think it's really cool that they're trying to like actually figure out or, you know, put this into the context of real life.
So they tried also to make sure that like the speed, like Simon said, that the flow of particles was matching what you would expect from someone breathing into the mask also.
Normally, or like under moderate exertion, like after a jogging or something, you know?
I also wonder if there was some kind of effect with like how far the mask is from the output of the air, you know? I don't think they mentioned that.
Why would there be though? The mask just filters through it.
Yeah, but I guess I don't know if like, you know, this distance here matters, even though you have some sort of closed chamber.
I don't know why that would matter, right? If the mask, it's just like you measure the concentration before and after the mask, and you compare the two.
Well, don't the particles like kind of diffuse around once
but I think
they get spit out?
I guess, but go ahead, Simon.
I just thought they knew the initial velocity of the air going in to the mask.
Yeah, I guess.
I think what really matters is the number of particles that get through, right?
Yeah.
Yeah, sure.
So the efficiency just gives you the number of particles compared to like the number of particles that go in compared to the number of particles that come out. And you just compare that with a concentration. But if you measure right before and right after, that's roughly the same as the number of particles before and after.
Yeah.
The concentration is just replacing number because you're looking at the same volume or whatever. I think.
Sure.
Or area, I should say.
Mm-hmm.
Also, another thing I found interesting is they mentioned that like there are like different strategies. I think Simon also mentioned it quickly, but that there's different strategies for like filtering aerosols. They said like gravity, inertial impaction, interception, diffusion, and electrostatic attraction.
Mm-hmm.
I don't know what inertial impaction is. I don't know if you guys is like a physics thing.
I think I can guess that it just means like if a particle is going in a direction and there's like a barrier blocking it, it just blocks it, you know?
Oh, okay. But what about interception though?
Yeah.
Oh yeah. Okay. Yeah. This is.
Or what about diffusion? I mean, I guess eventually, like as you get further and further away from the source, it's diffuse enough that you don't have to worry.
That's the thing. Yeah.
Yeah.
So, okay. Gravity is easy. Electrostatic is easy. Diffusion, I think, is quite easy to understand. Yeah. Then the difference between inertial impaction and interception. I'm going to guess interception means a particle is going somewhere and you intercept it.
Yeah.
Inertial impaction means there's something there and it just hits it. There's no interception. You're not moving something to block it.
Okay. I see.
That's what I would guess.
All right. Yeah.
Because inertia just means like its momentum is just carrying it in some direction.
So they say for aerosols that are large, the first two mechanisms play a role. So
by the way, we can look this up.
Gravity, sedimentation, and inertial impaction, where ballistic energy or gravity forces are the primary influence. And then as they get smaller, then you get diffusion by Brownian motion.
Mm-hmm.
And mechanical interception becomes a thing. Okay, yeah, so whatever. If they're big, they just like fall and that's it. Okay.
Yeah.
If they're big, there's obstacles and they hit the obstacles and get trapped.
Yeah.
If they're too small, the obstacles can't, they pass through the obstacles
Yeah.
Because the obstacles are too big to catch them, these small particles, and you need something else, like some attractive force with electrostatics.
Cool. All right, makes sense.
That's I think the main point, yeah.
All right, so then we can get into the results, I guess.
So this is figure 2, yeah, where they have they're testing here natural silk, a single layer of natural silk at the resting breath rate of 1.2 CFM. And basically, so they're testing this as a function of particle size, as we mentioned, and they here on the top is the upstream concentration of the particles, and on the bottom is the downstream. And I guess, I mean, there's nothing really. All we observe here is, there's a decrease from the upstream to the downstream, right?
I think before
B and D. Yeah.
Sorry, I think we should just mention though that the types of materials we're looking at. So looking at cotton with different thread counts, and that's supposed to be good for like this mechanical filtration. And then they look at things like silk and what else? Silk, flannel, and chiffon, which are supposed to be like electrostatic materials that could intercept smaller particles.
But this figure, they're only looking at silk, right?
Yeah, but I think the point is there are more big particles that pass through the silk somehow, right?
Yeah.
The small particles
get
really cut off. The silk, you can see that the silk is already filtering the small particles quite well.
But one second, because B and D are in log scale on the y-axis, right? So
that is true, actually.
I'm not sure.
No, that's right, and it's arbitrary units for both. I guess you can just compare B and D. Oh yeah, but you see that B and D, the thing doesn't change very much, right? There's not much filtration.
But it does change by.
But those
like
are particles
on
also,
the log
right?
scale, it changes.
Yeah, but let's say it's like 50% or something, maybe, or 30% difference.
I found this graph hard to read quantitatively, so I'm not. All I see qualitatively is a decrease.
Sure. Okay.
I'm not sure. I'm not sure. Did they say something about filtering better?
It's more visible, I think, on the next graph. But
wait up though. B and D is
definitely.
10 to the 3 nanometers, right?
That's the size of the size of the particles.
So that's microns at that point, right?
Yeah.
So it's not. Is it showing that it's not having a big effect on large particles?
Right. Well, Simon's point is, you see this one, the top graph B.
Yeah.
It's above the line. Like the first bar is above the line. On the Y scale. Yeah. And in D, it's like it's like 80% of that.
Okay.
Or something, but it's log scale. So the in B it might be like 200 compared to 80.
Yeah.
It's very hard to see from this graph. I kind of agree.
Cool.
Maybe they said something in the text, but I might have missed it.
It's fine. I think the point of this, like you said, is just to show there's a decrease, and they show the real results in the next graph, in the next section.
Right. Yeah. So let's go to this graph here. So here in figure 3A, they are measuring the efficiency, which has to do with the concentration that you measure upstream and the concentration versus the concentration you measure downstream.
They define it in the materials and methods section. If you just want to scroll.
Yeah. It's like a ratio, right?
Upstream minus downstream over upstream.
Yeah.
Okay. Cool.
So 1 means 100% of the particles got filtered out. 0 means they all got through.
Yeah, exactly.
You said over downstream. You said
over upstream. It's like the initial.
Over upstream, right?
Final minus initial over initial.
Okay. Yeah.
So efficiency of 1 means nothing gets through. Efficiency of 0 means everything gets through, and then it's linear between that.
So here in A, they're measuring cotton with different thread counts, and they also measure for cotton quilt which they define as, it's like 2 cotton layers with 80 threads per inch or something, and some kind of thing in between.
Yeah.
They define it, right?
Yeah, I can look that up if you want.
Jamie,
I don't remember.
what is quilt? Often do-it-yourself masks. They have a high thread
Yes,
count.
it's 2 layers of cotton, sandwiching a cotton polyester, beading also some cotton polyester hybrid.
Mm-hmm.
Yep. Mm-hmm. And so as you can see, so this cotton 80 TPI threads per inch, it has pretty low efficiency, and they say in the paper this corresponds to people kind of making their own face
Is this
masks.
like a t-shirt, for example? I don't know anything about thread counts.
Yeah,
actually.
right.
I think they say like 600 TPI is something like a high quality bed sheet or something.
Isn't it crazy though that the very large particles, the efficiency is almost 0?
Yeah.
This was crazy to me. I thought it would be the opposite.
It's true, eh?
Yeah.
There's something weird.
Why does that happen now?
And for very small, maybe there's some
forgot.
electrostatic effects, just not as many.
Yeah, maybe.
I think they explained that too, and kind of.
Oh, did they?
I don't remember. Maybe I should have highlighted a lot more than I did.
No, it's fine.
Okay. And yeah, so that's that. And then, as you expect, when you have more threads per inch or a higher TPI, you have better efficiency. And the efficiency looks, I guess, pretty good. Although they have some pretty weird error bars, I would say, right? They say they get them from error propagation on that fraction, the difference over the upstream.
Yeah, so maybe the upstream has a huge error, and then like it's 1 over or something, or it's very small error or something, 1 over.
Yeah. Like they say sometimes they have like a very small number of particles, say downstream, right?
Mm-hmm.
So that, but I don't understand. Like, can't you just measure it multiple times, say?
But maybe it's limited by the device.
To get better.
Yeah, the
error on the machinery.
Yeah.
But
I see, right.
I guess the point is here though, it's like everything, the best you can do is this cotton quilt for small particles. And you're still roughly at 80%, right?
Yeah.
For the very small particles. And the worst thing, this cotton 80 threads per inch is like nothing. Like it's like it's really bad, right? For this huge range, the efficiency is 0.
Yeah. So this would be maybe like an argument against people making their own masks, right? And
yeah, I guess unless the particle is really like very extremely small or at a specific size, like at, I don't know, a couple hundred nanometers, it does almost nothing.
Yeah. Which could, and I think they thought it was like the spread was on the larger range at the beginning. And then they said like, oh, maybe aerosols play more of a role in infection.
And I guess aerosols are just very small.
Maybe that's why
So we don't really know why the cotton 80 TPI is filtering out aerosols, right? We assume it's because
I don't even know what it is. I don't even know that it is.
But look, it's at the average is at 60. It's at 50 something, right?
The average?
At the
I think it's
range.
electrostatic.
For the
is
green
it not
line at the top?
Electrostatic here, or no?
I don't think the cotton ones are electrostatic.
But why are they filtering out at such small sizes?
Yeah. So what I mean is it's 60%, right?
Yeah.
There's probably some electrostatic forces.
I think they do say that in the paper, actually.
Yeah, but what I'm saying is if COVID is anywhere between, I don't know, 30 nanometers to a couple hundred nanometers, this does nothing, right?
The y-axis, the x-axis is logs.
If the prime mode of infection is in that range.
And then if it's bigger than, if it's bigger than 1 micron, you also do nothing.
Yeah.
So if you're wearing a 80 TPI mask, you better hope COVID is in these ranges.
Yeah.
Otherwise, you're not doing anything, right?
I mean, this like blip in the middle, I feel like is some kind of weird error, no?
Maybe, but the error bars are quite small.
No,
Yeah.
yeah, there's.
I mean, why? It's weird. Maybe it like matches exactly the thread, like, you know, size, and that's the perfect thing that like fits through the.
I
It
don't
like
know.
traps the particles. I don't know. They don't really discuss that, eh?
No.
I think they might have. I'm not sure. They probably did, honestly.
I just read the paper.
Oh, really? And
Well,
they
they
didn't
say
say
it's
anything?
something about like electrostatic interactions are commonly observed in various natural and synthetic fabrics, polyester woven fabrics. Oh, but that's not cotton, eh? Oh no,
That's the yeah, that's the other ones. I
they
think.
retain more static than fat fibers or cotton. Yeah, okay. So they just say like single layer 80 cotton does not perform well, varying from 5 to 55% depending on the particle size. That's it.
Because if you look at the next figure, figure B,
Mhm.
there's a kink in the opposite direction at the same level.
Yeah,
Right.
that's true.
And I just thought that was a transition between electrostatic forces and like mechanical forces dominating the filtration mechanism.
Hmm.
So you expect it to go down as electrostatic force becomes less important, and then back up as the thread count takes over as the filtration mechanism.
Hmm.
But I don't know why there's an opposite level kink. Like in the green curve in figure A, I don't know why it boosts up and then goes back down.
Hmm.
Like I think it's plausible in figure B, this kink, but the kink in figure A is weird to me.
The thing is, it could,
Mhm.
like, if that's a legit effect and it actually coincides with where the virus is at,
Yeah,
I think like a 50 something percent filtration efficiency is probably at a population level not so bad, right?
sure. But you can get much better doing some very simple things, right?
I guess, yeah.
As figure B shows.
Yeah,
Mhm.
but I guess we just want to like know whether or not all the mask wearing people are doing is actually doing anything. But what I think is also more, I was interested in going into this is like the surgical masks. But I think like, I don't know, most people are wearing those, right?
Yeah, and that's going to depend
Yeah.
on gap, which
I think
we'll
very
get
few.
later.
Yeah. Okay, we'll get into that. But anyway, so yeah, the take home here is t-shirts are probably not the best if that's what their thread count is.
Honestly, when I look at this, though, the take home for me is like I want to be the best thing I could do. I think is the green curve in figure B, which is like 4 layers of silk,
Mhm. Mhm.
right?
Is that
But
the best?
they have
No.
they have some better efficiencies.
What about the
later
red
on,
curve
no?
in figure A?
The red curve in figure A,
It's better.
maybe, but at very low. Okay, yeah, okay. So it depends on the particle size, I guess. But because for very small particles, you dip to 80%, whereas this one
Yeah,
is like
that's
at
true.
95.
Yeah.
But yeah, okay. So I think the point is you can make some home masks that are quite good, actually.
Yeah. Also, the
Um,
breathability is a thing. I don't know, like if this cotton quills, you're just going to suffocate.
Well, they give you
I
the
think they
numbers.
have that in.
Yeah.
Yeah. So okay, so figure B here. I think so. These are all now electrostatic materials, or more electrostatic properties. So they have 1 layer of silk, 4 layers of silk, flannel, and chiffon. I don't know how to say it. Is it chiffon?
Chiffon.
Chiffon.
I
Actually, I
say
don't know.
chiffon, yeah.
Chiffon. Okay, chiffon. And so the first thing you see here is 4 layers of silk are obviously better than 1 layer of silk
Mhm.
in terms of efficiency.
At all ranges.
And yeah. And I'm actually a bit okay. I'm red-green colorblind, so but okay. The top curve is the 4 layer, right?
Yes, it is.
Okay.
What's interesting also is that
And
usually in populations, right, two people, everyone's wearing a mask.
Hmm.
So if I want to transmit to you and you're wearing 4 layers of silk and I'm wearing 4 layers of silk,
Yeah.
it's like 8 layers of silk or whatever,
Hmm.
So like,
Well, it multiplies, I guess.
yeah, I mean, we can do things, I think, with just like, you don't need anything fancy is my point,
Yeah.
If you had 600 thread per inch cotton and both people are wearing it, I think it's quite good.
Honestly, though, I can't imagine breathing through 4 layers of silk.
Well, they give you the pressure, right? It's not that bad, it looks like.
Okay, I guess I've never tried it. Yeah.
4 layers of silk is almost the same as one layer of chiffon.
Whatever that is.
They say it's like a scarf, like people would layer, like as they would layer a scarf around their face.
Yeah,
It's
yeah.
the same.
But that's full of holes, right? I guess we'll get to that. But when you're doing
Maybe,
like
yeah. But I think it's the same material, I think, though. That's the point.
Yeah, sure.
I don't know. So yeah, so in B, you see like the efficiency is like in general pretty good in the lower ranges due to the electrostatic nature of these materials, and there's kind of a decrease, I guess, because with particle size, because these are really good at electrostatic trapping, but maybe not as good in terms of impaction or interception, right?
I think the idea is as the particles get bigger and the momentum becomes larger, the electrostatics can't stop them as easily, because you need more, you need them to travel longer times to trap them. That for a given velocity,
Right.
it becomes harder and harder to trap things electrostatically. But eventually they get so big that the thread count of the silk or whatever can still stop them through mechanical forces.
I see.
So it goes
Okay,
down.
so there's like
it goes down as electrostatics becomes less important, but the particles are still quite small. But then goes back up as the particles become big enough that the mass can stop things mechanically. So I think
there's like a mesoscale effect here.
Well, I think that's why this kink is
of.
happening right at the sweet spot where it's like too small or too big for the electrostatic force to take effect, but too small for the for the mass to stop the particles.
Right.
So this kink makes sense to me, but the kink in the figure 8 makes no sense. The green one.
Right. Yeah. Maybe I have to read through again to see what they said about that.
Yeah, take home. I think Carlos said it right. Like t-shirts or 80 threads per inch might be bad, but like generally speaking, if you just wearing a mask seems to be quite good. At least it's stopping the virus. And
in the supplementary, I think they also investigate synthetic silk, and they find that it's a lot less effective.
So you really gotta
you gotta pay up.
You gotta pay up. Get that real silk. I have a good place on Amazon for real silk. I can put a link in the description.
Nice. You have an affiliation link or something? Or?
Yeah, you promoting?
Just free advice. Okay, so should we get to figure 4?
Sure.
Let's hit figure 4. That was a good figure. All right, here we go.
So here they're figure 4A. Sorry, so let me just move my notes here. Figure 4A, they're measuring these hybrid masks and N95. So N95, I guess if you don't know, captures 95% of particles over 300 nanometers. That's why.
Just to be clear, I think the reason they're using these hybrids, right, is because it's cotton and something else, because you want one material that stops things mechanically, and one material uses electrostatic forces to stop. So the idea is use both, so that you have a filter for both types of particles.
Yep. Yeah. So that's the idea that they had here. And so as you can see, like the efficiency is much higher than before. Also, I mean, in general, I guess. And the N95, I can't see with all these. I don't know these different colors. I can't.
N95 was the bottom one. Like it's the weakest one.
I think the point is that N95 is really bad at stopping small particles, but a little bit better than stopping large particles compared to these other hybrid things. So I think this kind of discourages. I think the take home from here is like, N95s are not the best thing. Maybe you can do better overall by a hybrid mask.
But we're gonna get to the
primary mode. Yeah,
I think N95s usually fit much better than like a homemade whatever.
Okay, yes, this is another factor. But if I just had a material to block things with, maybe I gain an extra couple % for very small particles, or very large particles, I should say. But I sacrifice this huge range for small particles, right?
So the N95, like, I'm also having trouble. It goes to the top, right? Like around the middle. Okay.
Yeah.
95. It goes to 95. I
No, it goes to like 1
Uh,
basically.
Well, here it
Once
goes
it
to
gets-
1 for,
Yeah.
but the particles are bigger, I guess.
Yeah.
Yeah. But so the thing is, that what did I want to say? Yeah. So I guess if the mode of transmission, if like most of the transmission is happening above 300 nanometers, N95 is still the best. But if
Yeah, but I mean,
not,
it's better.
then
It's better by a couple of percentage points compared to the second best, right?
Mhm.
Cotton and chiffon,
right.
it gives you a little bit more, but I'm also protecting myself from these
Mhm.
aerosols, which are much smaller if I use the hybrid.
Right.
And it's
But
like
if aerosols are not, Mhm. Go ahead.
yeah, so it's going from 70% to like 90% for very small particles, and still giving me over
Mhm.
90% efficiency at large particles.
So again, like I guess I just don't know where we're looking, what range we should be looking at. But yeah, like overall efficiency, it looks like these hybrid materials are better, right?
Area under the curve.
I
Yeah.
think just average or whatever.
Or average, sure, yeah.
Average of the points, yeah.
Yeah. And so yeah, so that's that figure. And here they're measuring with this gap, and so the gap has 1% of the area of the material they're using, surface area, and the dashed lines are the ones with the gap, and yeah, so they compare surgical mask to this hybrid cotton silk mask with and without the gap, right?
Mm-hmm.
And as you can see, with the gap, it's a lot lower, right? The efficiency. So it really does show that, you know, the fit like around your face is really important, right?
Mhm. And this is 1%, right? Which I'm confident
Yeah.
most people have at least 1% of a hole between the mask and their
Mhm.
face, right?
Yeah.
Right.
So we're looking at the efficiencies being like
Although
closer below 50%, you know, for a lot of these.
I don't know how these like how do the N95 masks, like, do they usually fit very, very well like on your face?
Yeah, they're like a cone.
I
I have one.
they're
It's like a cone.
They're
It's like a
very-
plastic thing, and it just goes over your mouth and nose.
right. I see. And
can't
like it's
deform it.
tight like on your,
I think it has these straps that
but
you
like
pull.
I mean like
Carlos
I
has
see,
one,
okay,
so he
yeah.
knows.
I mean, it's just that it has a structure. It's not like the fabric that's just like
Yeah,
it
yeah.
can be in any. So it just like sticks on. And also,
So
it's
it's
also
like
kind of comfortable actually because
fastened-
it doesn't like it doesn't press on your face. You know, like your nose can kind of move around. But also, it's annoying because
right, yeah.
you really can't like. There's very little air going out. I find. So
I see.
you know, I like to
Mhm.
put the mask like under my nose so I can breathe through my nose still, and you can't do that with an N95.
But Carlos, you shouldn't be doing that, right?
I
Because
think-
you're increasing the size of the hole from 1% to like 50%. You know.
No, I figure
if
like
you put it below your nose, you're doing nothing. You're not doing anything.
So the differential pressure when it's under my nose is a lot better.
But you're not doing anything though. Might as well take the mask off.
No, I know. No, that's not true though.
Yeah, because look, if you go to the table, Simon,
Mhm.
for these
Yeah.
gaps of like 1%, the efficiency goes down to like 37. Like the hybrid cotton silk with a gap, the efficiency is 37%.
Yeah,
Or
but look,
32%.
like you said, right? It's if everyone's wearing the mask,
Yeah.
it's 50% times 50%.
Yeah, but if everyone's wearing the mask with under their nose,
What are we
It's
looking
like-
at?
sorry.
9%. We're looking at 9%.
I mean, no, but like what I'm saying is, if 1%, if a whole of 1% drops the efficiency from 94 to 37,
Yeah.
a whole of like your whole nose, which is 50% of the surface
Mhm.
area, should drop it much more than that, right?
Yeah, sure. No, I was being cheeky, honestly.
No, but I'm just saying, like, your criteria for wearing the cloth mask under your nose compared
mean-
to N95.
Although there is like the sort of, it's asymmetrical, right? Like you want to, you're trying to not receive particles, but also you're trying to not emit particles. And I don't think you're emitting much through your nose. Whereas I think if you perfectly block everyone's mouths, then there's maybe not so much transmission going on, right?
Okay, I'm not sure about that. Maybe.
So I mean, that's for another episode, but that's what I think. Like, I'm not so concerned about myself getting infected, you know, but I understand the concern to like affecting third parties, you know. So then getting rid of things going out of your mouth is much more important, right?
I'm not sure.
I think we should keep the opinions out, right? We're trying to objectively review this paper, and I guess we should mention that I guess we all have very differing opinions on this subject.
No, I mean, really speaking strictly about like what to do about wearing masks. Sometimes I feel like, well, at the level of like being outside in a social setting, I think what you're trying to do is get rid of particles going out of people's mouths, really, right?
I don't know. I don't want to say anything because let's focus on this paper, baby.
I don't think this is controversial, but whatever.
No, but noses could be a problem also. We don't know.
Yeah, sure. I'm sure like aerosols come out of your nose, so that I could totally be wrong here. That's another paper we should look at.
I think we should just like yeah, sorry. Go ahead.
No, if you just look at the table though, you can see that like for small particles, N95s do not that great.
Yeah.
But for large particles, they do amazing. But surgical masks do like the same level, you know.
Wait,
with
surgical
no
masks with or without gap? No, there's a drop, right?
If you compare no gap to no gap, N95 to surgical masks,
sure. Yeah.
It's roughly the same, right?
Well, you 10% drop, although there's a huge error bar on the surgical mask.
Sure. But it's roughly the same, right? It's like
but then when you put that, like I think there's like an artifact that like in practice when you're wearing an N95 you have a smaller gap.
Okay.
I think like obviously I don't think they tested this, but
if you have a gap in N95s, it's worse than having a gap with surgical masks.
Yeah, that's true. I wonder why that is, eh?
I'm not sure either.
Huh. I mean, maybe surgical mask has some like electrostatic properties that the N95 doesn't have. I don't know.
Yeah, I'm not sure. And if you look at cotton, it looks like it's a beast, you know.
Cotton quilt, yeah, looks solid.
Cotton silk hybrid is like, for me, is the all-star of this whole thing. Right? But we got 94% and then 98.5%.
Wait, why didn't they do the holes with the cotton quilt?
Cotton silk, they did.
Wait, hybrid cotton silk, gap, no gap.
the
Okay,
third
sure,
from the
yeah.
bottom.
It's just that the gap ruins everything, right? And I think like in practice, you're more likely to have gaps when you home make your own cotton silk thing.
You don't have to home make it. I'm sure the companies sell.
Yeah, I guess
some kind of mask. Mind you, every time I wear a mask, there's always a gap on the side. Like I can't get rid of that.
Yeah. And the one for me was like the way when my nose is sticking out. That's another gap I can't get rid of.
Yeah, but I guess if two people are if two people are wearing the mask, though, this like 37% or whatever, I guess, reduces, right?
Yeah, for sure. That's the thing, right?
The best one is hybrid.
Hybrid cotton silk,
hybrid, right? Isn't it cotton chiffon?
Oh, right.
Chiffon?
Chiffon's better. Yeah.
Oh, sorry, that's the one. Yeah,
Chiffon.
that's the all-star.
Right.
But I think
if you want protection on all ranges, make a cotton chiffon. No.
But even above 300 nanometers,
well,
what you get from N95 is
it's very good.
0.7%. You know, and I'm sure this N95 is very expensive compared to this cotton chiffon.
Yeah.
But wait, the delta P though.
Do they sell these?
Check the delta P's.
Yeah, it's not comfortable. It's not very comfortable, I guess.
It's the N95 is the most comfortable.
But Carlos, you told us the pressure was horrible with N95.
Yeah, but it's because I wear the other ones with holes all over the place.
N95 is less comfortable than holes.
Yeah.
Than nothing.
The holes are crucial. Yeah. No, but when I will go to see my grandparents, I'm not going to do it this time. But when I do, I wear an N95 with no holes or anything. But you know, like I think, again, I'm drifting from like the mechanical experiment here, but there's like there's a population level phenomenon that you have to deal with, right? Like maybe 50% for everyone is good enough because we're trying to reduce like hospitalizations or whatever. So I don't know.
I don't know if we can say that right now. Yeah.
I think Imagine everyone wore cotton chiffon masks properly. I wonder
Yeah,
where we like
what world would we be
how
in?
much we could reduce.
Yeah.
Yeah. I wonder, do you know if they sell these hybrids also?
That's a good question.
I'm not sure. Yeah.
The authors of the
Because-
paper have already their own
because,
company
like-
that's selling them.
Yeah.
If these are cheaper to produce than N95, then maybe it's something that I
Alright,
feel like
Jamie's gonna
people
look it
should
up.
know about.
But I think the point is the fit, like Carlos said, right? N95 is easy to fit on your face probably. Whereas
Right, yeah,
these other
I see.
hybrid, like anything that's fabric, when I put the mask on, it's always like on the side over here. I have a huge like, it doesn't fit on my face perfectly, you know?
It's
Yeah,
because
yeah.
it's not rigid, right?
Yeah.
Yeah, maybe that's the point.
But they do have like
They're
I
not
don't know if you've seen
produced-
the ones that like really like stick to your face. That people have. They do sell cotton and silk face masks. It's like a whole thing on the internet.
There you go.
But
Mhm.
I don't know if you've seen these ones like that look they really like scoop up over your face.
Yeah, but
They're not like a square, right?
But there's still holes on the top.
On the sides there's a little hole, yeah.
Yeah,
But
and
I
it's
mean they
all
look
you need
pretty
is
good.
1% to ruin everything. That's what's
Yeah,
crazy.
that's true, eh?
It's a 1% hole, and you just ruin the
Yeah.
whole efficiency.
But like look, I'm gonna share my screen. Yeah, Simon, can I share my screen really quick? I'll let you go back to it.
Yeah.
Here,
So
this is
do
what
I
I'm
stop
talking
sharing?
about. Is what here.
Sure.
This is a cotton silk hybrid apparently.
But do you see?
There's a hole here.
Yeah, below her
Yeah.
ear, there's a
And
hole.
probably here is like all
Of course.
holes.
And that's more than 1% for sure.
Yeah. And then we can look
Mhm.
at like N95 masks.
You're done. You know, this is already done. You're dropping to 30% here.
Yeah, for sure. So this, yeah, so this is like, which is the one I have? I think it's like this. It's not even super perfect, eh?
And if it's not perfect, it's garbage also, right? It's 12% for large particles.
Yeah. They're like this. Exactly this is the one I have.
Basically, I'm kind of against N95 masks now.
Huh.
No.
Oh my God. Official stance
Please.
from Ozeki.
No, but look, it's 12%
No.
efficient for large particles. It's 12% efficient if there's a 1% hole.
But maybe it doesn't have maybe N95 doesn't have that much gap, right?
But what I'm saying is, I don't know. I think we should be recommending these hybrids.
Well, they should make a
Maybe.
hybrid that has a really like a structure to it, right? That can really fit to your face.
Yeah.
Anyway, I think we should just present this objectively and let people decide, right?
I mean, from the numbers, you can make a statement though of what you think should happen.
I mean, it's
Right.
pretty clear, right?
I mean-
Just from a materials point of view.
Yeah.
I mean, yeah, sure. I mean, if
If you
you
wanna go-
accept that, yeah, there's
If
a
you
few
wanna go
things you have to
95
accept,
route,
right?
I'm just saying, if you want to go the N95 route, you got to make sure that it's stuck to your face somehow, you know?
Yeah. I mean, we're just saying if you wear a mask, wear it properly, right?
Not
But
even
I
that,
think it's
though.
even impossible to wear properly,
That's
probably.
that might be the issue.
But apparently, so these N95 masks, they have like these, like they say in the paper, right? Like they have these special fitting like elastics or whatever. So
Yeah,
it's possible to adjust it to be like flush on your face, right? Or I don't know.
If you can write an N95 mask, basically you want to get the biggest number here. If the best you can do is N95 properly fitted, then you should do that probably.
I
Yeah,
mean, it's, yeah. And it's also, I don't think it's that expensive. In Mexico, you can get them for
But
really
it's-
cheap. Probably not real N95.
I think
It says
the
N95.
hybrids
N92
are,
or whatever.
I think the hybrids are really interesting though, because like I think people, once aerosols were, like once we knew aerosols was a mode of transmission, people were freaking out because N95s are not made to filter those.
Wait, do we know that
aerosols
aerosols are a
out,
mode
so-
of transmission, Simon?
I
think we do.
think, well, the CDC changed its guidance a while ago about this. I don't know.
Okay. They did say that aerosols can
Uh,
carry the virus and they can stay suspended. They cited that paper in this one, right? But from that to say that it's a mode of
definitely.
transmission, I don't know.
Well, I'm sure they have a lot of evidence for it. I mean,
Mhm.
I hope at least.
Yeah.
So this, I guess this paper really shows there is a way to get around this aerosol worry, maybe, right?
Yeah, for sure.
But maybe not in no, yeah, I guess.
So from the
and,
WHO,
yeah,
it says aerosol transmission can occur in specific settings, particularly indoors, crowded and inadequately ventilated spaces where infected persons spend long periods of time with others.
Which is not usually where you're wearing a mask, right?
Yeah.
Is the thing.
More studies are underway to better understand the conditions in which aerosol transmission is occurring outside of medical facilities, where specific medical procedures called aerosol generating procedures are conducted. So basically, there's a possibility. I guess we can't rule out aerosol transmission yet.
Right.
I guess that's the point.
Yeah. Yeah, I guess it's less of a worry outside, right? Say
I think everything is less of a worry outside because the concentrations are so low.
I see. Okay, yeah.
And there's also way more like, air flow and stuff like that, right?
Yeah, the ventilation is optimal.
Yeah.
So that's okay. So
should we recap it?
Yeah.
I think we did everything.
Yeah,
right?
yeah.
I don't
so
know
they
if I
have
had
this
any...
guidance.
Oh yeah, they wrote a little medical advice.
Do you want to share your screen?
I just wrote.
You can share your screen.
Oh, I'm not sharing.
No, I hopped into.
I'm not sharing right now.
No, you're not. Now you are.
Oh no. Okay. So basically what they say here, it's pretty obvious stuff. High threads per inch is better than low, right? For cotton. You can use electrostatic material for protection in the aerosol range, right? And hybrid masks can be useful for filtering these smaller particles because of these electrostatic trapping effects, and proper fitting is important. Right.
Excellent. And this is all supported by like physical experiments, right? It's honestly, not observational.
Yeah.
I think proper fitting is the most important, right?
Yeah.
It seems like from
it's
the
really
results,
important.
It's like the most important thing you can do is properly fit.
But the thing is, I think they say that like their study of the fit is kind of like cursory. They haven't like really dug into it. Like maybe the way they set up their experiment for testing the fit is like too removed from how it actually works. You know?
Okay, that's true. But it seems like a very small hole.
Yeah.
Can lead to a dramatic it's a crazy like how small the efficiency goes to with a 1% hole. You know.
Sure. Yeah. It's kind of interesting. I don't know. Maybe there's some sort of physics there, like the pressure difference on because of
like
the
a funnel or something.
Yeah. I wonder, like, I think they have to study that a bit more, right? But I think they're just sort of ending it on like that's probably future work.
We can probably check from recent papers.
Could you make is it possible to make an experiment with like people doing this, like a controlled experiment with like masks?
Well, there was one from
seeing
Denmark,
like the aerosol concentration.
Oh, like in a lab?
Oh, I'm. Oh, okay.
Well, I saw this paper in Denmark, right, where they did like they gave 3,000 people masks and told 2,000 people not to wear masks, and then they did PCR tests to see like which ones got more infections, and in both settings, like they were all in the same country, and there was the same like social distancing measures, and they couldn't find a significant difference in infections.
Oh. Okay.
Between the two groups, but I don't know. I haven't read that paper closely.
What kind of masks did they give them?
I think surgical, but I'm not.
I'm wondering if like the gap just plays a huge role, right?
Yeah,
like these gaps on the side, like maybe they're 10%, you know, and then it's like the efficiency goes to 0.
Okay, sure, yeah. So, but the thing is, they saw like it was something like 1.8% infections in the mask group, and like 2.1 in the no mask group. You know, there's a very small difference in like just not having a mask at all. So maybe like having that gap is almost the same as not having a mask.
Yeah, that's what I'm saying.
Yeah, okay, you're right. No, I don't know enough about that study, but I think that's the only one that I could find that was like a controlled study of mask wearing. But we can like find others that might be interesting.
And why can't they put like a test dummy, you know, and like with a real face, put the mask on to get the real gaps, you know?
That's what I'm wondering. Yeah.
Do the same experiment, you know? So you have the physically the gaps are at the same locations and they're the same, width and whatever, and you can do the same experiment and measure how efficient the masks are for those types of gaps.
I think for this one they had like two sections, right? They had like pre-mask and post-mask, and they could measure the difference in concentrations. But I think like if you have this like dummy, you have sort of like a cloud going around the dummy, of virus.
No, but just put the dummy's mouth on this tube.
Yeah.
And then put the mask on his face. And then you can measure inside the dummy's head.
In the dummy's head. Yeah, you have to go into the dummy's head.
That's fine, right?
That's okay. The dummy's fine with it.
It's a dummy.
It's a dummy. Yeah, it's true.
It could be a person too, no? I don't know.
Well, how do you measure the concentration inside him? Maybe there's a way. I don't know anything about this.
Yeah, honestly, I don't know like how
the PCR test tells you, I think. PCR gives you the load, the viral load, quantitative PCR.
So they just to end their paper here, they also, I just wanted to say that they mentioned that they didn't study humidity, like the effect of humidity.
Sure. Yeah.
On like
temperature, I guess.
How
right?
this.
Mm-hmm.
Yeah.
Or like wind currents, atmospheric pressure, maybe.
Because I remember reading like humidity works against the virus, right? So I guess I don't know. Is that true?
Kind of makes sense to me.
If that's true.
Not sure.
Maybe like air particles,
so
water particles filter like others, in the air.
I remember this was why they were saying in winter, like with a drier environment indoors, it's going to spread more easily, right?
Yeah. But I guess in these conditions, like in the conditions of the experiment, it would be like optimal infection conditions for the virus, right? It's like a closed chamber with like no external airflow. So it's kind of like an upper bound, I guess, on transmission. As soon as you any other factors are going to just make it worse, right, for the virus.
No, one sec though. All you care about is filtration through the mask. It doesn't matter if it's ideal condition for the virus to survive or not. You just care about how much virus goes from outside the mask to inside the mask. There's no upper bound here.
Sure, okay, fine. But I think like that saying, for example, that the mask filters 50%, and then maybe like humidity takes care of the other 50%, Sure, I'm saying like in the real world, at the end of the day, it's hard to measure
how getting sick.
Yeah, for getting sick. Yeah.
Okay, sure. I don't think they care about that. They just care about like how effective the mask is.
Sure. That's why I'm saying it's an upper bound, right? Like
at getting sick.
Yeah, at getting sick. Sure, yeah, for sure. At getting sick.
Maybe. I don't know enough about that.
Me neither. Okay, well, that's
and they also
go on, Simon.
Sorry. The last thing they mentioned, they could have also studied how washing the masks affects the efficiency. So I guess you would expect it to deteriorate as you wash it more and more, right?
Makes sense.
Yeah.
And
I never got like the point of like of not reusing masks, like surgical masks. Why can't you just use them forever, or for like a long period of time? Do they degrade, or do they like build up virus that then like gets stuck and gets like shot out or something?
I'm not sure.
That I'm not sure. Maybe it's a worry about getting infected.
Yeah.
From the mask.
They do start to like decay though, eh? The surgical ones. After a few days, that like the strands kind of like come out.
They get frail up and they.
Just by breathing through them.
I think it's because it's like a lot of little fabrics, like little fibers, so they start like falling apart. I think. I don't know.
Yeah, I mean, I think those masks they're not meant to be worn multiple times, right? Also.
Yeah.
They're supposed to be disposable. But here, like because of shortages, I guess, or whatever, people are reusing them.
If you go to the hospital, they make you take off your mask and they give you a fresh mask.
Oh yeah.
They want to make sure that you're wearing a fresh mask, I think, for exactly this reason. Like the mask you're wearing could be like destroyed by the time when you're wearing it in the hospital.
Yeah.
There must be something with these reusing these surgical masks.
That's for another episode.
Yeah.
We have
And-
a few other episodes lined up now.
These guys are from the Argonne National Laboratory in the U.S.
Do you know it?
Yeah, I know. Well, I know what the Argonne National Lab is.
Oh, I don't know it. What
Is
is
it? It's a government funded lab. It's like
Like NASA?
is that a lab? Maybe.
I don't know. Like Mila? Or
I don't know. Is it
PI?
government funded? Maybe. Yeah, sure.
Perimeter Institute?
It's just a government lab, I guess, where they do these type. I guess I don't know. This is interesting to me because they're trying to make quantitative assessment of what you could be doing to limit your exposure to a virus.
I also learned about the whole electrostatic thing. I didn't know that was a thing.
Yeah,
I didn't know
that's
that
true.
either.
And I'm surprised you can catch like 10 micrometer size particles, right?
You mean 10 nanometer?
Nanometer, yeah. That's tiny. That's like
Yeah,
that's like proteins are that big, I think. Individual proteins.
yeah, it's craziness.
Really, individual proteins are that big? Interesting.
I don't know.
Yeah. I remember like when I was doing molecular dynamics, I was dealing with like a 1 nanometer radius chunk of protein.
1 nanometer radius. That's okay. So it's much smaller.
Yeah.
10.
No, but like there are proteins that are much bigger. Let me Google this really quick. COVID size. How is that? You think that's going to tell me how big the virus is? What size is the coronavirus? Quora.
For sure 10 nanometers.
Or is going to tell you?
You think it's going to tell me?
I don't know. I know Google will tell me.
I'm on DuckDuckGo, so we're going to erase.
COVID size.
0.5. So the measure between 0.05 and 0.2 microns in diameter.
Wow. So it's like 500 nanometers.
Yeah.
Wait, 0.05 you said?
Yeah, 0.05 and 0.2 microns.
So it's 50 to 200.
So say like 0.1 microns, right? So is that 10 nanometers?
It's 100 nanometers.
100 nanometers. Yeah, so there you go. You can catch the virus, just the virus itself. Forget about being in a droplet.
That seems huge though. Okay, I don't know.
What do you think of like this study versus like, so I think they do like country studies, right? Where like they have they compare like mask wearing in a certain country to others, right?
I think those are hard to understand, hard to like parse out other effects, no? But I mean, I don't know. There's probably some stats there. But usually like when there's countries that are enforcing mask policies, they're also enforcing other policies.
Yeah, right.
So you don't know what's the cause. That's why like I found this Danish study interesting. Maybe we can talk about it.
Yeah, right.
What do you think of them though?
Cool.
Like is that kind of study sort of more the foundation for like your opinion on wearing masks?
I completely agree with you that, if the country or whatever, the state like says, you have to wear masks, then that same place will probably say, you can't have gatherings.
Yeah.
So it limits it. So again, like this is the first paper I read very closely. Mm-hmm. So I'm not sure what the argument is, but
yeah, we should look at more.
I would, yeah.
The thing is,
I think so,
yeah, I don't know. We can do another episode if you want on like more population level studies. Would be cool to like sort of compare that or like have that together with this one.
Mm.
All right. Well, Perry, any other thoughts?
No, I was looking at the size of the corona. I found here it says 20 to 500 nanometers actually.
Yeah.
So 0.02 microns.
Yeah.
To half a micron.
Mm-hmm. Okay. Well, I was on Quora.
It's kind of a huge range. I don't know.
I don't know why it's a range either.
Yeah, me either. I would feel more comfortable if the government gave me some information like this, like, by the way, like if you wear this type of mask, this is the efficiency you get for this, size or whatever.
Yeah, I agree.
Like just telling people to wear masks, I think is kind of misleading because now it's like you can see here, if you wear a mask with a gap you can get screwed.
For sure. But I think like there's just a big gap between like science and policy, I guess. And they're probably like trying to just cover as much ground as possible.
I don't know, but we spend a lot of time asking politicians like, will Christmas happen this year? Instead of asking them like, oh, by the way, this mask recommendation, what is it?
Yeah.
Like why? Like I don't know.
What's behind it? No, I agree. But even this study, right? Like,
but it's definitely better. It's better to wear a mask, right? And like the lower.
But maybe they could tell people like wearing one layer of
effective.
cotton is stupid. You know, guys, don't wear one layer of cotton.
They should. I think there should be more quantitative like involvement with the public, you know, like they should know what to expect. But maybe people don't, you know, people are looking more like, should I wear a mask or should I not wear a mask? And they don't want to worry about.
I think you're right about that, Simon. And I also think like, even if you do give quantitative, like, you know, backing, it's also very like, I think interpreting that quantitative data is often like, it takes some training, I find. So
that's true.
I think, not everyone is going to be like,
That's why people should listen to this podcast to really get like that kind of, you know, understanding scientific.
But to
thought.
hear you say that, they have to listen to the podcast in the first place.
That's true. That's
you know
true.
What I'm saying?
But I don't know. Sure.
But 1 second, I think most people know that N95 is better than like just a cloth face mask.
But it depends for what, honestly. We just found out. Also, people at one point were just saying like, make your own masks, you know, like make your own mask. And then you see like, make your own mask of one layer of cotton is like 9% efficient. Well, thanks, you know.
But this was,
I'm wearing a mask for nothing now, you know.
I think this was more like when there was a shortage, but maybe now people are relying
this paper
more
came out in April, right? Like 1 month after the pandemic started.
Yeah.
That's when people were making their masks,
globally.
you know.
Not
like
thinking about the whole
guys, cotton masks don't do anything. And you know, if it's 9% with no gap, imagine there's a gap, you know.
But I think this study, like, it should make people like question what material mask they're buying. Like maybe you think more about the thread count and blah blah blah. So
but also there's a big part of this is we don't know like what particle size matters, right?
Well, apparently it's a huge range also, right? The WHO, or I don't know which site I found this on.
Yeah.
Newsmedical.net. Okay, I don't know if this is reliable. 20 nanometers to 500 nanometers is the size of the COVID.
But 1 second, is that including what particles they hitch a ride on? Like what kind of?
No, I think that's the raw virus, right?
Yeah.
Oh, that's the raw virus.
The droplets. Sorry, let's see. 5 to 10 micrometers are the droplets. So an order of magnitude larger than that.
Right. But there are some aerosols are also important, right? Like below that range.
I guess so. But I guess 20 nanometers is the limit, right? And here they're actually looking. Oh no, it's about 10 to 20 nanometers. Is the 10 nanometers is the smallest size? Is the smallest size here? So I guess it's consistent with that study or with that information of 20 to 500.
And then the other thing is like what's the actual added benefit of having a mask in the population, you know, in practice? Well,
I think if if it's efficient at stopping the virus, the benefit is that you infect less people, no?
Well, no, because you have other options, right? For like, I don't know, social distancing and things like that.
Okay, but this is like a huge thing, like economic and
everyone.
I know.
Ecological issue, you know?
Yeah.
Everyone just stay home. And
there's also like how does it work if a particle gets through the mask, right? Like what's the distance that it's still relevant, that particle is still relevant, you know?
I think we're not looking at we don't know really what viral dose is needed to infect someone, right? Like
we really don't.
But I think they have studies about that too. Like you spend like 10 minutes in this proximity with some type of whatever. They for sure did studies like that, right?
I mean, they've also found people that live together that don't have COVID. One person has COVID and the other person doesn't. meaning that the viral load has
Yeah.
to, like, some people live together and one
Yeah.
person gets COVID and
Mhm.
the other person doesn't, right?
Yeah.
So that
That
means
happens.
that happens.
Okay.
So that suggests that the viral load is quite large for this, right?
Mm.
So that's a separate issue,
Or
I think.
maybe that other person also was like like maybe they had the virus previously and they didn't know, right? And maybe they have
I
some
guess that's
sort of
possible.
immunity.
I guess it's possible, but I think there's suggestions that the viral load is quite large for COVID.
And they also do like
I see.
contact tracing, right? And they show that most of the infections are happening at homes, in homes, like houses, and where you're, like you Perry said, you're indoors for a very long period of time, versus like
thought
you're
they
at the
were
grocery
coming-
store. I don't
but-
have
but-
I don't have
okay,
studies
wait,
for this.
so
Just Joe Rogan.
So we live in Quebec, and most of the infections were coming from work and schools, right?
Aren't the
Yeah, but
majority
at
coming
work
from
you're
this?
indoors, in an office for a long period of time. It's not like you're going to the grocery store or you're going like shopping to.
Sure. But it's on a private home, right? That I don't know. Maybe they.
Yeah, I don't
I'm
know
not
about private homes actually. I would imagine like that's where if you're living with someone who has the virus, it's super likely. I mean, that's the most likely you can get to getting it, right? Again, no data to support this whatsoever.
We should cut all of this out of the podcast. The podcast should just be the paper.
I don't know. Editing is a bit annoying. No, okay. I think this is an interesting discussion, but it just means that we have to do more episodes and more reading about this, right?
We don't know anything.
Yeah. I don't think it's good to like put our we don't know anything. Sure.
Yeah, no, okay. So let's
that
wrap it up. And thank you, Simon. That was really nice. That was a really nice episode. I had fun. I learned a lot, and we have a lot to do for the next ones.
There you go.
And Happy New Year, guys.
Cool. Yes, Happy New Year. Thanks.
Happy New Year. Are we ever going to finish Alien Frontiers also?
End.